It's pretty wild when you think about it. Some of the most powerful algorithms in the world, they don't start with some impossibly complex idea. Nope, they often start with something so simple, so human, that you use it every single day without even realizing it. Today, we're going to go on a journey, starting with a basic series of questions and ending with a powerhouse algorithm that has totally dominated competitive machine learning. So, let's dive right in.
Okay, picture this. You walk up to a busy restaurant. Do you wait for a table? Your brain just kicks into gear, right? It starts firing off questions. Is it packed? Yeah. Okay, what's the wait time? Over an hour? No way. But what if it's like 20 minutes? Well, am I starving? Yes. Is there anything else good nearby? No. Okay, I'll wait. See that little flow chart of yes or no questions? That's how we get through life.
So this process, this simple game of questions, it's just second nature to us. But here's the cool part. That's not just a neat human trick. It's actually a fundamental concept that we can teach computers, and it's the key to unlocking a really powerful kind of machine learning.
And that brings us right to the heart of it. That little flowchart you just ran through in your head, in the world of machine learning, that thing has a name. It's called a decision tree. And, as you're about to see, it's a shockingly powerful idea. So how does a machine actually use this? Well, let's imagine we give a computer a whole mess of data about fruit, their width, their height, whatever. And we want it to learn how to tell a lemon from an orange. If you look at this graph, they're all just kind of mixed together. The challenge is, how do you teach a machine to draw a line and separate them cleanly? Okay, now this is where it all clicks. The algorithm does the same thing we did. It just asks a simple question like, is the width more than 6.5 centimeters? If the answer is yes, it draws a line. Then it asks another question, is the height more than 9.5? And it draws another line. Each one of those questions creates a split, a decision boundary you see on the graph. And if you follow those questions, what do you get? You get a tree. It's a beautiful, visual way to see the logic being built. So if we're going to get formal about it for a second, a decision tree is just a model that makes its predictions by splitting the data over and over again based on different features. It follows a path down this tree-like structure until it lands on a final answer. Simple as that. All right, so we have our decision tree, and it's making predictions. Great. But what about when it's wrong? Because here's where it gets really interesting. It turns out that not all mistakes are created equal. In some situations, the kind of mistake your model makes matters a lot. Let's really raise the stakes. Imagine a model that's trying to detect a serious disease. Now, it can mess up in two ways. It could tell a perfectly healthy person that they're sick. That's a false alarm, right? Scary, but fixable. Or it could tell a sick person that they're perfectly healthy. It could miss the disease entirely. Which one of those is worse? I think we all know the answer. And it highlights a huge challenge in machine learning. To really talk about this, we need a little bit of shared language. For any prediction like this, there are 4 possible outcomes. A true positive is when you get a yes right. A true negative is when you get a no right. But the errors are what we're focused on. A false positive is that false alarm. And a false negative is the one we really worry about, the misdetection. It's all about managing those last 2. And that leads us to 2 of the most important ideas when you're judging a model like this: precision and recall. These 2 things help us measure and, more importantly, help us balance the kinds of mistakes our model is making. Let's start with precision. The best way to think about it is with a spam filter. Precision asks a simple question. Of all the emails that my filter yelled spam at, how many of them were actually spam? If you have high precision, it means that when your filter flags something, you can pretty much trust it. It's all about not having false alarms. Recall, on the other hand, is asking a totally different question. It asks, of all the spam that actually hit my inbox, how much of it did my filter manage to catch? High recall means you're really good at finding all the stuff you're looking for. It's all about not missing anything important. And here is the classic tug of war. If you're building a fraud detection system for a credit card, you care a lot about precision. You absolutely do not want to be blocking people's legitimate purchases all the time. That's a surefire way to lose customers. But for medical diagnosis, you want to crank up the recall. You would much rather have a few false alarms that require a follow-up test than miss even one person who's actually sick. The problem you're solving tells you which one matters more. So a single decision tree is powerful, but it has a bit of an Achilles heel. Sometimes it can get too good at memorizing the data you train it on. We call that overfitting. And then it doesn't do so well on new stuff it's never seen. So what's the fix? Well, what if instead of relying on one tree, we used a whole forest? This is the big idea behind something called an ensemble. Think of it like the wisdom of the crowd. Instead of asking one so-called expert for their opinion, you ask 100 of them. Any single tree might make a weird mistake, but what if we built hundreds of simple trees and just had them all vote on the answer? The final prediction is just the sum of all their little predictions. It's a much safer bet. The fancy term for this is a tree ensemble model. By mushing together the predictions from a ton of individual trees, you end up with a final model that is way more accurate and way more reliable than any single tree could ever hope to be. This is a cornerstone of modern machine learning.
So for years, data scientists were playing with this ensemble idea. One of the best techniques is called boosting, where each new tree you build is specifically designed to fix the mistakes of the trees that came before it. And all of that work, all that iteration, led to an algorithm that just completely took over.
Meet XGBoost. The name stands for Extreme Gradient Boosting, and it wasn't just a small step forward, it was a giant leap. It was an open-source system for this tree boosting idea that was so effective, so scalable, it just started setting new records everywhere. It became the new state-of-the-art.
And look, you don't have to take my word for it. Let's look at the scoreboard. Back in 2015, on Kaggle, which is basically the Olympics for machine learning, 17 of the 29 winning solutions used XGBoost. I mean, come on. That's not just a popular choice. That is absolute total dominance. It just became the default weapon for anyone who wanted to win. As the original paper itself says, it became the de facto choice of ensemble method. This wasn't some toy algorithm stuck in a lab. This was a battle-hardened system being used by the best in the world to solve the hardest problems out there.
So what was the secret sauce? It was just brilliant, top-to-bottom engineering. XGBoost was designed to be screaming fast. We're talking over 10 times faster than the popular alternatives at the time. It could scale up to handle datasets with billions of data points. It had this clever built-in way of dealing with missing data, which is a massive headache in the real world. It was a perfectly engineered system that just solved a whole bunch of problems all at once.
And that brings us right back to where we started. We began with a simple, human way of making a choice, just a flowchart of questions. We saw how that evolved into a decision tree, how we learned to manage its mistakes with precision and recall, and finally, how bundling up thousands of those trees into an incredibly optimized system like XGBoost created an algorithm that could win against anyone in the world. It really makes you wonder, doesn't it? What other simple, everyday piece of logic is out there, just waiting to become the next huge breakthrough?